In 1731, English astronomer John Bevis pointed his telescope toward the Taurus constellation and noticed a faint, glowing cloud in space. This cloud would later be catalogued as Messier 1, or the Crab Nebula. Unlike the nebulae we studied in our last lesson, the Crab Nebula is not forming stars. Its name is simply a leftover relic from a time when astronomers referred to any mysterious fuzzy object in the sky as a nebula. But if it's not forming stars, what is it? Over 200 years later, in 1928, Edwin Hubble gave us the first clue. He began to compare images of the nebula taken years apart and realized that whatever it was expanding, growing bigger each year. Astronomers started to suspect that the nebula could be linked to a rare event that had occurred in that same section of sky nearly 1,000 years earlier. In 1054 CE, ancient astronomers recorded a new guest star in the sky. It was so bright that it was visible in daylight for weeks. By the 1900s, it was understood that these ancient astronomers had witnessed a supernova, the violent explosion of a dying star. Modern astronomers studied the Crab Nebula's gas and dust, tracking how fast it was expanding. When they worked backward, the pieces lined up perfectly. This was the aftermath of that ancient supernova, a star's explosive death echoing through space and time. Today we know the Crab Nebula as a supernova remnant, the final burst of a massive star's life. But not all stars end this way. While some die with cosmic fireworks, others simply fade away quietly. In this lesson, we'll explore what happens when stars die, and why their final act depends entirely on one thing: their mass. Let's start with small stars. These stars live long, steady lives, fusing hydrogen into helium during their main sequence stage. When the fuel runs out, they begin fusing other elements and slowly swell into red giants, shedding their outer layers in what's known as a planetary nebula. What remains of the original star is a small, dense core called a white dwarf. No more fusion happens. It simply cools slowly over time. That's the quiet, gradual death of a low-mass star. For massive stars, the ending is far more dramatic. These stars burn through their fuel quickly. Once their hydrogen is gone, they expand into a red supergiant and continue fusing other elements, much like their smaller counterparts. But when fusion stops completely, the show begins. Gravity causes the core of the star to collapse, triggering a powerful explosion called a supernova, just like the one witnessed in 1054. The outer layers are blasted into space, and what's left behind will either become a neutron star or a black hole, depending on the star's mass. A neutron star is what's left behind after a supernova for some stars. A neutron star is so dense that a teaspoon of it would weigh as much as Mount Everest. It's made almost entirely of neutrons, hence the name. Neutron stars have incredibly strong magnetic fields, and many spin rapidly, becoming pulsars that emit pulsing beams of electromagnetic radiation that is detectable from Earth. But for the most massive stars, like the O-type stars we looked at in a previous lesson, not even the outward pressure from the neutrons can stop the gravitational collapse after the supernova. The core of this kind of giant continues to implode, becoming denser and denser until it forms a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. So mass decides everything. It determines whether a star dies in peace or in violence, whether it becomes a cooling ember, a spinning ball of crushed atoms, or a tear in the fabric of space-time. While that might sound like science fiction, we see the evidence for all three outcomes across the universe. But what about the star we know best, our sun? Where will its fate fall? Let's take a look at what we know about it and how we can predict its end. Our Sun is still in the prime of its life cycle as a main sequence star and has enough fuel to continue fusion for about 5 billion more years. But even still, it won't last forever. So which path do you think our Sun will follow when its time comes? Will it go out quietly, ending its journey as a white dwarf? Or will it end explosively in a dramatic supernova? To answer this, consider how our Sun compares to other stars in the universe in terms of size and temperature. Pause the video for a moment, and based on what you know, predict its fate. We know the Sun isn't one of the universe's giants. It's not an O-type or even a B-type star. Compared to the monsters out there, our Sun is actually pretty average in size, and maybe even a little below average. That means it's not massive enough to end in a supernova, so it won't collapse into a neutron star or form a black hole. Instead, its death will be quiet and prolonged as it slowly whimpers away. The Sun will first become a red giant, engulfing some of the inner planets. If any civilization is still left on Earth at this point, its only hope will likely be evacuation to a different solar system. The Sun will then shed its outer layers, and what's left behind will be a white dwarf. At this point, it won't shine because of fusion, but rather because it's still extremely hot from all the energy built up during the star's lifetime. Over billions of years, it will cool and dim, eventually becoming what's known as a black dwarf. A theoretical object, because the universe isn't old enough for any to exist yet. But what about more massive stars? The ones that eventually become black holes? Let's take a closer look at an example of a star whose fate was very different from the fate of our Sun. Cygnus X-1 was first spotted in 1964 and was the first object widely accepted by astronomers to be a black hole. It's about 6,000 light years away from Earth. Because it orbits another massive blue supergiant star, its existence as a black hole was given away by the stream of gas it steadily pulls in from its companion star. Cygnus X-1 obviously had a very different ending to its life than what our Sun will eventually experience. How did it end up here? Millions of years ago, Cygnus X-1 was a massive O-type star, more than 20 times the mass of the Sun. Like all massive stars, it burned through its fuel quickly and underwent a violent supernova explosion, which was triggered when its iron core collapsed under the immense force of gravity. But why would its core have been made of iron at this point? We know that stars are made primarily of hydrogen and helium. What do you remember about the process of fusion that could explain this? Remember that once a star runs out of hydrogen, it can then do fusion with helium, then with heavier elements like carbon and oxygen. But once the sequence works its way to iron, fusion stops, because fusion with iron would require energy instead of releasing it. The end of fusion is what puts the star into its final death throes. The supernova explosion that resulted from the end of fusion on Cygnus X-1 blasted the star's outer layers into space. But the explosion wasn't just a cosmic light show. Its immense heat and pressure forged heavy elements like gold, zinc, and uranium and sent them deep into space. These are elements that can only be created in the extreme temperatures and pressures of a supernova, and their scattering allows them to become part of future planets, stars, and even life. After the supernova, what remained of the original star was a dense core, too massive to even become a neutron star. Instead, it became a black hole. There's no return from this point. Any matter or energy that gets too close will never be seen again. In an upcoming lesson, we'll take a closer look at black holes and consider what a journey near one would be like. Every star you see in the night sky will one day face its end, either going calmly like our Sun, or more dramatically like Cygnus X-1, and the star that formed the Crab Nebula. But as with life on our own planet, it all exists in a cycle. One star dying sends out raw materials and energy that spark a new star's formation. And thus, the story of our universe continues. And we'll continue our story of the stars next time. Until then, keep stargazing, and remember that what you see in the sky is only a brief snapshot in time of our universe's history. Hey!